Hi class, we're going to take a look at section 7.8. Before we do that, I've got a diagram for you to look at. So take a minute and meditate on what you see here. See if you can figure out what this diagram is showing. It's quite cool actually. If you haven't done that yet, I encourage you to pause the video and take a look. You can see we're plotting some interesting things on the horizontal and vertical axes here. We've got the trace and the determinant. Now the determinant for a square matrix is an object that you know well. The trace is, I think I did make some mention of it a long time ago, but it's a pretty simple quantity to calculate. You can see I've set it on the slide here. It's a good, you can see we're always kind of trying to smuggle in some linear algebra terms throughout our multivariable calculus and differential equations study, right? The trace of a matrix is just, like it says, simply the sum of the diagonal elements. So, and you can see that this corresponds, this quantity that it says up in the corner here, corresponds to the, well, the discriminant. That's often why we use like a capital delta to denote that, like kind of delta for discriminant of this is for a matrix, a 2x2 system. So its characteristic equation is quadratic, like we've seen so many examples of. And that quadratic has, for its discriminant, if you were like use the quadratic formula, the part underneath the square root would be this quantity, where the trace and the determinant are computed in the way we have described and that you know well. Give it a try with a matrix, and you'll see that that always comes out to be the determinant. So you can see all the different cases that we've been talking about are nicely illustrated here. Like if that discriminant is, for example, less than 0, then you know you're going to get non-real roots. Well, if that's true, then you are in these places in here. If it's equal to 0, then you get, well, I shouldn't tell you. That's what we're going to discuss today. Our lesson lies along this parabola here today in this trace determinant space. It's kind of a fun little plot. But take a moment, if you haven't already kind of done so, to study the rest of this diagram. There's a lot of interesting things and a lot of the cases that we've already dealt with that you can find in this picture. A lot of these should look somewhat familiar to you. Okay. All right. Well, let's dive into our lesson today. We're looking at 7.8 repeated eigenvalues. Again, it's that situation where the discriminant of, for at least a quadratic characteristic equation for a matrix, a 2x2 matrix, where we have repeated eigenvalues. So there are two cases that we can discuss, and honestly, these are cases that work for larger matrices too, not just 2x2 ones. The first case is that we have, this is kind of an easy and trivial case. If you do have repeated eigenvalues, it could be that you're dealing with the identity matrix. Now, if it's a 2x2, if it's a larger matrix, it's possible that it might not be quite as obvious, but the key is that it's self-adjoint. So if you don't know what that is, don't worry about it too much. For a 2x2 matrix, it's really just going to be like a scalar matrix by the identity. And so in that case, you can pretty quickly check what the eigenvalues are here and that they're repeated. Just even in your head, can you see that the eigenvalues, if you have a diagonal matrix like this, the eigenvalues are just going to be the values on the diagonal. So let's just show you why this is such a simple case. The case 2 is really what we're going to get to in a minute, and it's going to be the main subject of the lesson. It's kind of the trickier one. But you can try this. I don't have all the details here. I just trust that you know you're good at finding eigenvalues now. But remember, you're going to find the eigenvalues first. Of course, it's going to be 3 and 3. And then remember, we're going to like take the matrix and then on the diagonal subtract the eigenvalue. So what your matrix will end up being in this case, your like eigenvalue problem matrix, is it's going to be 0, 0, 0, 0. Like when you subtract 3 on the diagonals from this matrix, which already has 3's on the diagonal, you're going to get this result for your eigenvector that you're looking for. The eigenvector needs to have like 2 components to it that satisfy this equation. Oh my goodness. Could we find some? Well, of course, anything works for that, right? Anything at all. So provided these are linearly independent vectors, you can actually pick anything you want for these vectors in this case. So this kind of covers case 1, where we have repeated eigenvalues. That is what's happening here. You have repeated eigenvalues. But it's kind of in a really trivial way. You could use like 3, -2 for this one. And over here, 10, 17. Those are linearly independent vectors. And so that would work too, right? It makes sense to pick easy ones like I did, though. Okay, so that's kind of a simple case 1. Case 2, though, is the one maybe we're more concerned with. And that is, what happens if such a nice thing that we just talked about doesn't happen? If that's true, then we're going to need to use something called a generalized eigenvector. So you can see that you're going to trust me on this, okay? For a proof of this, you can see your book. Just because, I don't know, I always debate how deeply to go into all the linear algebra and stuff. And I also think there's like a strong intuition based on previous learning in our course, like what we do when we have like a repeated solution and we're like looking for other independent solutions. We remember that happening with quadratic, with second order linear differential equations when we were studying those back in chapter 3, right? And like the second solution we got by just like taking the first solution and multiplying by a t, right? That's like, you're kind of seeing a little bit of a hint of that here in this solution. And we're going to work through an example here, so there's a lot more to say, obviously. But the other thing we're going to say is we're introducing this crazy Greek letter xi. We've already introduced, and we've kind of mentioned that. That's the eigenvector that you're going to get. You're going to get one eigenvector off of this. So this first part, there's really no story to tell there. And it also appears here, and all the r's are the single eigenvalue that you have that got repeated. This vector here, though, we need to discuss. What is this guy? It's the Greek letter eta. I've got a little highlighted Greek letter thing. I'm not sure if you've used that one in your life before, but it's kind of like a cursive N, but like the second part is like longer. The second, it actually descends below the baseline, kind of like a lowercase p or a lowercase q or something. It kind of goes down below the baseline. You can kind of see that here. See how it goes below the e? Anyway, that is called a generalized eigenvector here. And this, notice that what it does is it satisfies an equation that's very similar to our normal like eigenvector problem. But instead of equaling 0, it's equal to our other eigenvector, which we already found. So we're going to like solve this. So that's what we're going to kind of now unpack with an example. So just to motivate this, the kind of matrix we're talking about here, if we're talking about 2x2 matrices, is maybe one like this. Notice that this does still have, you can check it, please do, that still does have a repeated eigenvector, a repeated eigenvalue 3. Yep, definitely. But now it's not so clear. This is a defective matrix, right? It's not so clear what to do after that. It is much clearer and easier and simpler up here, right? In this case where you have this very simple equation. You can start trying to work through this without me guiding you, but think about what would you do in that situation. All right, let's do an example. By the way, the example I'm about to do is not the same matrix that I just introduced, 3, 1, 0, 3. It's a different one, but the same kind of issue comes up. So just want to make sure you're not thinking that I'm switching it out on you. I am switching it out on you, but. All right, let's get into it. So here we go. We've got a system of two differential equations. And now we proceed as we usually do, as if nothing bad is going to happen. But you can see why I've set this up here. Because as you go to do this, I'm going to skate through the details. You'll see that the characteristic equation gives you only one eigenvalue. It's a repeated eigenvalue. Okay, so far we can still find an eigenvalue. We have it, the eigenvalue. We can find an eigenvector that goes with it without too much trouble, right? Do the thing we normally do, plug into up here and here, okay? And, let what happens. Remember, we're just going to get like information off the top row, or if you want the bottom row, that's fine. Either one is going to give you the same relationship that this has to hold. So it looks like we've got our eigenvector pair, but it's only one pair. So we're going to have to figure out what to do after that. But there we go. We got one of them, though. That's something. And that is an important part of that solution that we wrote out. So let's keep that in mind as we move forward. How do we get that second linearly independent solution, though? That's now the thing that's sticking in our craw here. Let's get into it. So I'm put up here again just because I'm sure we don't know it by heart yet, but maybe eventually we will. We've got the form of the solution which I suggested in a box on the previous slide. So we're going to try and follow this kind of approach. Let's see if we can do it by plugging in the things we already have. So here's the thing we're going to use. We have A, we know what that is. We have I is the identity. 2 is, for our problem, 2 is the eigenvalue, remember. And C is our eigenvector. So plugging all that in, and I've got eta 1, eta 2 here as our elements of that additional generalized eigenvector. And you can see I'm doing all the things we normally do. Okay, so this is different here than usual in only one respect. We're going to now have on the right side, like it says here in the note, you're going to have, instead of 0, you're going to have -1. Notice that once again, you get the same relationship from the second eigen. You get the same relationship from both equations, right? So again, you have a dependent matrix here. So you just, again, only need one line of the matrix to help you get this. I just multiplied. It looks like I took, kind of looks like I did row 2. Obviously, row 1 gives you the same thing, though. You get eta 1 plus eta 2 equals -1. But the top row would be the same thing. It's just multiplied through by -1. Okay, so now we have a relationship between those two. And honestly, Mr. Chase, I thought you said this was going to be hard. It's pretty clear that we could take, for example, n2 to be 0 and n1 to be -1. Notice we can do that here. Normally we can't do that. Because normally we say, like, when we're finding normal eigenvectors, we have like C. If we said, you know, usually C2 is like 3 times C1 in a normal eigenvector. Well, that won't work. If you pick 0 for one of the elements, one of the entries in that matrix, the other will be automatically 0. You won't get the scaling you want, right? So eigenvectors we want to have non-zero parts to them. We can pick this to be free. We don't have to pick 0 for one. I'm just saying that in this particular case with this kind of generalized eigenvector, we actually can. And now we can finally write our solution. Let's look at all the constituent parts of this. Okay, so we've got, this part is not a huge surprise. We came into it knowing that this was like part of our solution that we needed, C1 times that thing. There's our eigenvector and eigenvalue that we got like then in the normal way. The second part, though, kind of follows this form that I'm suggesting here. C, that eigenvector column vector, is the same thing here. Notice it appears just here again. And then all the r's, everywhere they appear, are 2, so that's not a surprise. And then we've got this vector, which again there's some free choice on it, but I chose to do 0, -1, and I put that there. Or, sorry, -1, 0. And feel free to take the time to do it. I won't, but I encourage you to do it, to check that this really is a solution to the original system of differential equations. Let's also think about the phase portrait for a moment. First of all, you can see, because the eigenvalue is positive, that it's going to be unstable. It's going to, like, just think about what happens when you put larger and larger t values in. Is this going to head toward the equilibrium? No. So here's some phase plots for the phase portrait on the left here. This is kind of how the phase portrait looks. And you can see that the eigenvector is in there that we expected. 1, -1 is kind of this guy along here. All arrows, of course, are headed out away from the equilibrium here. And then this other generalized eigenvector gives you this kind of, I don't even know how, this kind of curving motion as well. Sample plots of this, of these curves, depending on the constant C1 and C2, are shown in the diagram on the right. And that is called an improper node. It can be stable too if the eigenvalue is negative. All right, with that, that will wrap up 7.8 for us. Really, you need to spend some time working out some examples and seeing what this is like, but I am kind of handing you that formula. So thank you guys.